All right, so now we're doing section 4.4, and this is going to be covering the main concepts just for time's sake, I guess, since we're on week 9 already. I'm only going to focus on 2 theorems out of the section, and so I'll leave it up to you to read up on. So if you go through the section in the textbook, I'm leaving it up to you to read up on the mean value theorem for integrals and the average value of a function, just to save time, because I think it's more important right now to cover what we'll be using applying into the next section, 4.5, and then also once you get into Calc 2. So the fundamental theorem of calculus, and there's 2 parts. Part 1. Most people really just know the fundamental theorem of calculus part 1, and I'll abbreviate it as FTC and then Roman numerals 1, or sometimes I just abbreviate as FTC. And essentially the fundamental theorem says that if you have a continuous function on a closed interval, and then you have the capital F is the antiderivative of that function on the closed interval, then the definite integral of the function is equal to capital F of V minus capital F of A. And so what you're going to do is you integrate the function based on integral rules, find the antiderivative, and then you can plug the antiderivative using the bounds of the integral. And it's usually the upper bound of the integral B minus the lower bound of the integral A. So the benefit of this is you no longer have to apply the tedious limit definition where the definite integral was the limit n goes to infinity of that Riemann sum. This is going to take a lot less work, and an analogy would be that when we dealt with derivatives, first taught the limit definition of a derivative, and then you learned the derivative rules. And so once we knew the derivative rules, you no longer have to apply a limit definition. All right, so this is going to be way less tedious, but to do this, though, you have to know the integration formulas from section 4.1. And on Blackboard, I put up that derivative and integration table. So this video is assuming you know the integration formulas. And as an example, in part 6 video of section 4.2/4.3, we use the limit definition to find the definite integral from -1 to 1 of x cubed dx. And what we got was 0 as our answer. So from part 6, this came out to be 0 using the limit definition. So now I'm going to apply the fundamental theorem of calculus and get the same answer. So the fundamental theorem of calculus, we just use the integration rules. And I wrote down the integration formula for x to the n, and you just add 1 to the exponent and divide by that value. Now for indefinite integral, it turns into the antiderivative plus some constant of integration c. It's going to be a little bit different when you do a definite integral. So I still apply the same rules. I add 1 to 3, so it becomes x to the 3 plus 1, and then I divide by that same value. So that's 1/4 x to the 4th. Now notice now I put this in brackets, and around the brackets, on the right side I have -1 and 1. So I put the lower bound of the integral, lower limit of integration is -1, and then I put the upper limit of integration 1 up top. So that's a difference in what it would look like. So normally if we had just the indefinite integral of x cubed, we would have wrote it as 1/4 x to the 4th plus c. But really all we're focusing on is that part. So no longer we care about the constant of integration. So focusing on just the antiderivative portion, what I did now is I factored out the 1/4 and focused on x to the fourth. And then based on the fundamental theorem, we do capital F of B minus capital F of A, where capital F is the antiderivative. So we got the antiderivative to be x to the fourth, or 1/4 times x to the fourth, but you can factor out the 1/4 and just focus on the x to the fourth part. And so then in brackets, you'll see 1 to the fourth minus negative 1 to the fourth. So our A is the lower value negative 1, our B is the upper value 1, and you just do the upper value evaluated with the antiderivative minus the lower value. So that's what I wrote in green, f of B minus, or capital F of B minus capital F of A. Well, that's going to be 1/4 times, and that's 1 minus 1. 1 to the fourth power is 1. Negative 1 to the fourth power is also 1. We call that if you have a negative number in parentheses raised to an even exponent, it becomes positive. That would be positive 1, but I have the other minus sign that's in between. So 1 minus 1 is 0, times that by 1/4, you get 0. So notice that was a lot less steps. I'm not sure if you remember from the previous video that it took me a while to get to that same conclusion of the same answer of 0. So this process is called evaluating the definite integral. And just a thing is that if you have a definite integral, it's going to equal a number. An indefinite integral equals a family of functions. All right, that's pretty much it for the fundamental theorem. You can use the fundamental theorem of calculus to find the area under a curve, provided that the function is positive on the closed interval AP. So you just evaluate it just like we did, and then do the upper bound with the antiderivative minus the lower bound evaluated with the antiderivative. And that difference will give you the area from x equals a to x equals b. Again, that's if the function is positive. The definite integral itself does not have to be positive. So the fundamental theorem of calculus is a less known one, abbreviated FTC2, says that if you have a continuous function on an open interval I containing a, then for every x in that interval I, we have the definite integral, if you take its derivative with respect to x, of a to x, and then f of t dt is equal to f of x. And so they use a different letter t in the integral to not confuse it with x. So there'll be kind of two separate sort of variables, but it still ends up being the function f of x. So I guess I like to think of it as you take the derivative of an integral, you get back a function that's inside the integral. And so as an example, I demonstrated if you had, let's say you had capital F of x equal to the integral from 0 to x of t plus 2 dt. So I'm going to integrate it using the integration rules. So for t, that's t to the first power. So you add 1 to that, that'd be t to the 1 plus 1, and you divide by 1 plus 1. And then integrating 2 is making use of this one integration rule. So if we have 2 dx, that's 2x plus c. Now the difference is I have the letter t because my variable of integration is t. So you have 1/2 t squared plus 2t. And then notice I have that pattern of it being in brackets. And then I put the lower value of the integral 0, and then the upper value on the top part of the brackets x. And now I apply the fundamental theorem. At this stage, f of b minus f of a, and b is x, so it's 1/2 x squared plus 2x, that's the f of b part. And then f of a, well, a is 0, so you do 1/2 times 0 squared plus 2 times 0. So that whole thing in parentheses is the f of a or f of 0 part. All right, so it's capital F of x minus capital F of 0. And you simplify that, well, the 1/2 0 squared plus 2 times 0 part, that's just 0, so you can just ignore that. That's all 0. And you're left with just capital F of x is equal to 1/2 x squared plus 2x. So now if you take the derivative of this, so you have to remember your derivative rules, and make sure I did it right. So for derivative of x to the n, that's n times x to the n minus 1. Derivative of x is 1. You'd have to remember the derivative rules. So if we differentiate 1/2 x squared plus 2x, you get 1/2 times the derivative of x squared. Well, derivative of x squared is 2x to the 2 minus 1, using that rule. And then plus 2 times the derivative of x. Derivative of x is 1. So simplifying that, the 1/2 and 2 cancel out, so you just get x, and then it's to the first power, which is x, and then plus 2, because 2 times 1 is 2. Now notice capital F prime of x, the derivative is x plus 2. That is the same thing as what our inside of the integral is t plus 2. So it's the same thing, it's just we have the letter x versus letter t. So that's a demonstration of the second fundamental theorem of calculus. All right, and that's it for this video. Again, I'm leaving it up to you to read up on the mean value theorem and average value of a function. I think it's more important we focus on the fundamental theorem of calculus and its second fundamental theorem. And the following videos, I'll go into more examples of these.